Hello students, welcome back. Let's resume our discussions on linear models. We went through simple linear models. Now let's go to piecewise linear models. What do you mean by that? The rate of change was the key. The rate of change must stay the same if we have a linear model, but sometimes they change. But they don't change instantaneously all the way, but they may stay constant for a certain period and then stay constant for another period like that. In that case, we may get multiple linear models and we may have to put them together, kind of like this example. So in first interval here, highlighted in blue, we have the rate of change of 2, the slope of 2. Next, second interval, pictured in red, we have rate of change of 1. And the third interval here, pictured in green, we have the range of change of 1/3. Slope 2, 1, 1/3, like those. These kind of things can happen. Now, most of the time, these are coming from real-life models, so most of the time you're going to get continuous functions, but not always. You may get discontinuity, but most of the time you won't have to worry too much about discontinuity. Okay, here's an example. I got this from textbook 2, 2018 tax rate schedules. Schedule X for single and Schedule Y1 for married filing jointly or qualified widower. And we have a bunch of intervals from taxable income of 0 to 9,525 for singles, and we have a certain linear scheme because we have 10% here. That's the tax rate which stays the same, so 10% or 0.1. This one is the average rate of change, this one here. And the next interval, 9,525 to 38,700, we have another linear model and we have 25. What am I saying? Not 25, 12% or 0.12. That's the rate of change. And then we have the next rate of change of 22% or 0.22 and so on. And then of course we have corresponding table for married filing jointly. We have similar tax brackets here, but similar tax rates here, which are average rate of change. But the intervals, the tax brackets are of course adjusted accordingly. Okay, let's answer these problems. Let X be the taxable income and express the tax due based on Schedule X for singles here. Just rewriting everything, you see. Tax rate here is the average rate of change for that interval. So that's the slope. And then actually I'm using the slope point equation. You see, if you're making precisely 9,525 and nothing more than that, then any excess of 9,525 with this 12% of tax rate, none of them is here. So your Y value, the tax value is going to be 952.50 right here, and so on. So these are all slope point equation of the line. I'm using, let's see, I'm using this form all the time, except that I change the order. I use y0 plus m times x minus x0. I use the other order. I switch the order of addition, and I think that's easy to see. You see, y0 comes here, and then m, and then x minus x0. You see, from here. So slope point forms are being used here, and then those for each interval. Now, it is your job to do the same thing for married filing jointly. We have these intervals here, or tax brackets, and then the tax rates. These are the slopes. And then you can use slope point equation of a line for each interval, and then you can get the piecewise defined model here like this, piecewise linear model. If you do it right, you're going to get something like this. And then you're going to be ready to answer problem C. Suppose that a husband had a taxable income of $35,000 and his wife had a taxable income of $40,000. What is this household's tax if they follow Schedule X as two singles, married filing separately? And then do the same thing for Y, married filing jointly. And then you have to answer which is better. Use your common sense. Married filing jointly will be probably better. The answer is yes. As a matter of fact, I've been writing this kind of problem for quite some time, and based upon the older edition of the textbook, there were some loopholes. So in some cases, married filing separately was better. Most of the time, married filing jointly was better. And sometimes people used to call it marriage penalty or something, but those loopholes were recently filled out. So at this schedule, it will be very, very difficult, if not impossible, to find any example that married filed separately as two singles is actually better than married filing jointly. If I simply tell you the answer, it goes like this. So 3,500 for, 35,000 for husband, that falls into the second bracket here. And then 40,000 for wife falls the third bracket here. So we used the second line and the third line, and then put together and add them together, we get the tax of 9,849. Now, if you use married filing jointly here, you can add them up, 35,000 plus 40,000, which is 75,000. And that falls in the second bracket here with 12%. And add them together, you get 8,619. It makes sense because here, part of the income, a little bit portion, but part of the income is being applied with 22% tax. But here, no, not really. Some are 10% up to 19,050. And then the rest is 12%. And no 22%, so married filing jointly is better in this case. Anyway, piecewise linear models do exist, and tax rate, those are perfect examples. There are a lot of other examples too, and if you go to my math lab exercise set, you're going to see plenty of those. Okay, now let's go to linear regression models. Previously, I raised this question: how do we get this kind of models to begin with? Now, for tax rates, they're coming directly from the law, so the model is not really model. It's a law. So people just decide it. But sometimes we have something going on in nature, and then we have to model appropriately using some linear functions and approximate the best way possible. How do we do that? And that kind of thing is called linear regression. Now, this thing belongs more to statistics than algebra, so I'll just give you some pictures and I'll just move on. Our textbook has a little bit more problems associated to this, and then asking you to use technology. I'm not going to go too deeply into that. In short, if you have some large data, you're going to get slope point equation like this, and then x bar, y bar are means, the averages. So running through the average points, and then the rate of change, the important part, the slope, can be calculated by, oh my goodness, this formula, how am I going to calculate that? That's a completely different issue. I'll simply show you the pictures. Okay. These are monthly averages of daily high temperatures of these cities, Dallas and New York, Dallas and Los Angeles, Dallas and San Francisco, and so on, from 1914 to 2020, based upon NOAA website, which I went through there and painstakingly getting those data and then processed myself. So this picture in the program belongs to myself, so I don't have to worry about the copyright of anything or anything at all, even if I publicly express this in YouTube. So it's okay, because this program belongs to me. Anyway, as you can see, we have nice linear correlation between the two cities. As the Dallas high temperature goes up, New York high temperature also goes up, and as you can see, each dot, which represents a month, those are really tightly packed around a certain line of best fit. This kind of line is called the regression line, and the technical way to get this formula is right here, whatever that thing is talking about. But if you use technology like I did, you can get it. Of course, it's going to have to run through the average point. So the average temperature for Dallas is X coded. Average temperature for New York is Y coded. This one is for Dallas and Los Angeles. And still we have nice linear pattern, but a little bit less densely packed. So previously here, if you make a prediction, say for example 90 degrees in Dallas, and what is the best prediction for New York, that's going to be the point on this red line. And the real temperature, the real monthly average must be some gray point somewhere here, going straight up or down. And that error is relatively small, and here that error is going to be relatively big because we have fatter football-shaped oval. And this one is Dallas and San Francisco, and then even fatter here. Still, we have a nice linear pattern. Dallas and Honolulu. Now, it's somewhat linear pattern, but in this case, it's hard to make any kind of prediction. You see, the dots are really far away from this line of best fit. So if you make a prediction based upon the point on the line, which is the best way to minimize possible errors, but the error will be still significant if you do it this way. Compare that with Dallas and New York. The dots are really tightly packed. Yeah, okay, we're up to here, Dallas and Honolulu. Up to now, all those cities are coming from Northern Hemisphere, so they have positive correlation, but this time Dallas and American Samoa, which is in Southern Hemisphere, it's in South Pacific. In that case, we have negative correlation. So seasons are reversed, so that's what we're looking at. Anyway, the linear models like these, those are actually coming from a bunch of data and then finding appropriate way to minimize those errors. And that's how we are getting the linear models to begin with in many, many cases. And that's where I'm going to stop. I'm not going to do any kind of regression problems here in this course. Those pictures were nice because it gives you kind of theoretical understanding where in the world these kind of formulae came to begin with. Eventually, they came from extensive studies like these, and then numerically we got some linear models, which is pictured in this particular case green, and in this case brown, things like those. But exactly how to work with these regression lines is something I'm going to cover in a different course, Math 1680, Elementary Probability and Statistics, not here. So I'll stop here, and let's meet again in Chapter 7, in Module 7, excuse me, where we're going to deal with quadratic functions and quadratic models.